If a point be taken outside of a circle and two lines fall from the point on the circle, one of them cutting the circle and the other one just falling on the circle, and further, if the rectangle contained by the whole of the straight line which cuts the circle, together with the straight line intercepted on the outside from the point to the convex circumference, be equal to the square on the line which falls on the circle, the line which falls on the circle will touch the circle. Circle, point D, which is outside, and we're going to draw a line cutting the circle, and then we'll have another one which falls on the circle, and let's say it falls on it at C, we'll call this E and A. And so our given is that our primary given is that the rectangle contained by the whole of the straight line which cuts a circle, so AD, and the line, the straight line intercepted from the outside from the point to the convex circumference, so that's DE, if this rectangle is equal to the square on DC, then to prove is that DC is a tangent line, meaning it touches the circle. So I'll just write that DC is tangent. Step one. I'm going to draw a line that actually is tangent to the circle. So from, say at this point, B, line DB is tangent. And then utilizing proposition 1 of book 3, we'll find the center of the circle. We can call it F. And so center F. And then from F, we're going to drop lines down to C and another one up to B. And from proposition 18 of book 3, we know that since BF is a radius and it hits the tangent line, it will do so at right angles. Hits the tangent line at the tangent point, it will do so at right angles. So the angle DBF equals a right angle. We're also going to draw a line DF. So because of proposition 36 of book 3, since we know that the rectangle contained by DA, DE will be equal to the square on the tangent. Therefore, I can write up that rectangle DA, DE equals the square on DB. But we know from our given that the rectangle DA, DE is equal to the square on DC. Therefore, by common notion number 1, we can say that the square on DC is equal to the square on DB. DC squared equals DB squared. Which means that the line DC equals the line DB. And we know that the line FB and FC are equal because they're radii of the circle. Therefore, the two lines together, DC line DC and the line FC will equal the two lines DB, BF. And we know that DF is common. If you look at the triangle DBF and DCF, DF is common to both triangles, and DF is common. Therefore, we've got two triangles, DBF and DCF, each with three sides respectively equal. So we can say from proposition 8 of book 1 that all the respective angles, namely the ones which subtend the respectively equal sides, will be equal. Therefore, from prop 8 of book 1, we can write up that the angle DBF is equal to the angle DCF. But the angle DBF, as we showed in step 3, is a right angle. Therefore, the angle DCF is a right angle. But from the porism of proposition 16 of book 3, we know that when a line is drawn from a point and it meets the radius or the diameter at right angles, that line will be touching the circle. So it'll be tangent to the circle. Therefore, we know that DC is a tangent line, and that's exactly what our to prove was. Q